Good morning, everyone. Sorry I couldn't be there today. I had to make a quick trip to Tennessee for a family funeral. It's just one of those things that kind of comes up that you have to do, and I'm sure everybody here would do the same thing. So, fortunately, in our modern age, we can put together still a little quick video lecture to help out with learning and teaching, and I hope I will help you guys out today with this lecture. So what I did is took the notes that I was going to talk to you about today in class, did a little screencast of it, gave you a few examples of how to do things, and I think it's going to be about 30 to 45 minutes, something like that. You still have plenty of time afterwards to work on the problems, and then I promise you that on Friday when I come back, I'll go over homework from last night and from this assignment as well. So before we get going, I just want to also say that I still want to do burritos on Friday. I hope you guys maybe want to do the same thing. So if you guys could organize that together as a group, that'd be great. Hunter, we put you in charge of picking up the burritos. So if you could also maybe make a spreadsheet up, or not a spreadsheet, but make a list up of people that want to order burritos. So what we need, guys, is your name, how many burritos you want, if you want hot, medium, and or mild green chili, and then don't forget to pay $2 for each burrito. And then Hunter, if you want to come into ICE on Thursday, we can work out the details in terms of ordering it and all that. So anyway, that's it. We'll go ahead and get started with the notes, and if you guys have any problems, you can send me an email, or you can also use your book as a resource. The book pages I gave you, chapter 23, are going to be a good resource for this as well. So everybody have a great day, and I will talk to you soon. Okay, so last time we learned about this cool thing called refraction, where when light goes from one medium to another, it changes speeds because of the absorption re-emission process. And we also learned that one of the cool side effects of that is that when light does refract, it'll also change direction. So on this slide, I have, a couple pictures basically showing like refraction of light going into a square block, and you can see that when the light comes in here from the left, it would want to just go in a straight line, but because of that block, it actually ends up refracting. So when it gets to this point, it ends up changing direction, goes towards the normal when it's in the block. If I drew a normal line down at the bottom, you would see that the light actually is ending up going towards the normal at that point. And then that light beam continues on through the block, and then when it hits this surface, now it basically just refracts in the opposite manner. And if I draw my normal line here on the block and move it to the point of refraction, you can see that now that ray ends up refracting away from the normal. So one of the things that's pretty cool here from a geometric sense is that because this side and this side are parallel to each other, the geometry of it works out to where the light ray that emerges at the end is really just parallel to the original light ray. And I don't know, one of the things that you can use optics for is to look at like the path difference for what the light ray would have done if the block hadn't been there, and what the light ray did do because the block was there. And I mean, there's all kinds of very, very small things that can be measured, very small thicknesses that can be measured because of refractive properties. Like you could figure out the path difference between a light ray as it goes through a microscopic surface, and then because of that you can measure the width of the surface. So there's a lot of applications of that, but we don't really want to study that too much right here. What we do want to do, though, is look at what happens when light goes into a different material where the surfaces aren't parallel to each other. So down here in this bottom lens, you can see we've got a picture of a curved lens. This particular lens is called a convex lens because of the shape that it has. And you can see that these light rays that come in from the left, they also refract, but when they come out the far side, these light rays aren't parallel to each other. And basically that is just simply because the normal line at the top part of the lens is not parallel to the normal line at the bottom part of the lens. You can see from the normal lines that I've drawn on here that this top light ray is refracting away from the normal. This bottom light ray is refracting away from its normal. And if you look at this angle and this angle, you can see that, you know, those are equal angles. The law of refraction with Snell's law is still true, and light's refracting out at a particular angle based on the angle of incidence that it had inside. However, these light rays are not parallel to each other, and they end up bending to a spot. You saw this occur basically in the lab that you did, where you would take a lens and have all the light rays go to a single point. That single point right there is called a focal point. Okay, so let's go ahead and talk about then how a lens can actually take refracted light and make an image of an object at that point. Really, a lens is just a device that's designed to do that. You can send light through all kinds of different materials, but they won't make images. Images will only be formed if you shape the refracting material in such a way that geometrically it'll make the light rays intersect in a certain manner. The point that you have to understand here is that images are formed because of how our brain interprets the light rays. You know, if two light rays come from the same place and they intersect again later somewhere else out in space, or if they even appear as though they came from a certain point in space, then your brain perceiving those light rays will actually think that's where the object was. You know, I want you to imagine when you look at yourself in the mirror, you see yourself behind the mirror. Now, you're not really behind the mirror, you're in front of the mirror, but your brain thinks you're behind the mirror because the light rays that are bouncing off the mirror appear to come from behind the mirror. And so that's why you think you are in that position. The same thing happens with lenses. Lenses will either make light rays come together out in some place in space, and your brain thinks then that that's where the object is, when in reality it's just an image of the object. Or sometimes a lens will make it look like the light rays are coming from a singular point in space, and so your brain will think that's where the object is, when in reality that's just an image of the object. Boy, does all of that sound pretty confusing? Yeah, well, I agree so. But I'm going to show you some pictures here and some diagrams that will help to make more sense. You know, last thing to note here on the slide really quick is that there's really two types of lenses. There's lenses that are called converging lenses, and there's lenses that are called diverging lenses. Well, a converging lens also has another name. It's called a convex lens. And a convex lens is a lens that is thicker in the middle and skinnier on the edges. A diverging lens has another name. It's called a concave lens. And a concave lens is a lens that is thicker on the edges and thinner in the middle. When I come back to class, I'll get some convex lenses and concave lenses out so you guys can play with those a little bit. Okay, so these two diagrams basically show you how a convex lens and a concave lens make rays either converge to a single point or diverge from a point. And really that's why we call them the way we do, is because a convex lens like this, a converging lens, basically makes light all come to a single point in space, as long as the curvature is made in such a way to where it's nice and symmetrical. The converging lenses that you guys used in class, a lot of them actually had two focal points because the outside edges were bending light differently than the inside part of the lens was. Those are obviously cheaper lenses. The better lenses you can get will make the light come to a singular point. The diverging lens, the concave lens, actually makes light spread out from a point. So this isn't like a focal point per se. I almost like to think about it as a diverging point, but we still label it as a focal point. You know, when I think about diverging lenses and a diverging point, I oftentimes think about a picture like this. I remember when I was in high school art, we would be asked to draw perspective pictures, and so the whole idea was that you would draw a point in the middle of your paper right here, and then you were supposed to draw, you know, your scene or your picture or whatever as though everything was originating from that point, right? So It helped to give you like dimension in the pictures and that sort of thing. Well, I really consider that's kind of how a diverging lens does its thing. This is like the singular point in the paper where everything seems to come from. Okay, so look, this slide right here has some photos that I pulled off the internet that do a better job of showing like how a converging lens can make something called a real image, and how a diverging lens can make something called a virtual image. Up here in this top picture, we have a candle flame that is on this meter stick. This is like a kind of a common high school optics setup where you have these legs on a meter stick, and then you put a candle on the meter stick, and some distance away from the candle you place a converging lens, and then over here at the end of the meter stick you have a piece of paper that acts as a screen. Right, so what happens here is that the light that comes from this candle goes through this lens, it all focuses to someplace out in space right around here, and then you end up actually getting the image of the candle flame farther away than that actual focal point. And I'm going to be showing you a ray diagram process in a moment that explains why that would be. But the big thing to understand from this is that when you look at this candle flame, you may or may not be able to tell that candle flame is actually upside down. Whenever you get a real image that's created by a lens like this, you always get a projected image that's upside down, which is pretty interesting. Okay, now the other type of lens that we might think of in question, a diverging lens, can make like a virtual image like this, where in order to be able to see the image, you have to actually look through the lens and see the image. I'm seeing the image of the meter stick in the background. You can see that the image looks different than the object does, and actually looks smaller and sort of disproportionate. But that's an example of seeing an image that we would call virtual. The important thing to realize is that with this kind of setup right here, you actually could not see a virtual image. You might think that if you could put your eye like someplace over here in the background, and actually like look through the lens back at the candle flame, that you might actually see like a nice clear image of that candle flame. But it turns out that if we set that up, you wouldn't. If you actually put your eye over here and looked backwards, you might see like a blurry candle flame that would be upside down, but you wouldn't see a nice clear crisp image like you actually see projected on the screen. So it is possible to use a lens like this to get a real image, or to get a virtual image, I'm sorry, like I would in this picture. In that case, if I took that lens and set it up right here, I would actually see this meter stick look bigger, but that would happen because I was putting the converging lens close to the object. And when you put this kind of lens close to an object, you actually can see a virtual image that looks bigger. That would be like a magnifying glass situation. But when you set it up like this, that isn't what occurs. Okay, so back to the notes. The process that we use in physics to sort of explain and describe how images get made is a process of drawing ray diagrams. This is just a cool kind of old school geometric thing that does a great job of predicting where images will be formed, and also it kind of gives you a little bit of an understanding why images will be formed. So when you're drawing ray diagrams, it's important that you have a ruler handy and a nice sharp pencil. So as I continue to talk, you should probably get out a ruler if you haven't already done that, because you'll be using that here in the process of drawing ray diagrams in just a moment. So on this slide, what I have is I have the three sort of rules or guidelines that you follow when you're drawing ray diagrams. These numbered items are basically showing you the rays that you're going to draw when you draw these pictures. And when I do an example here in just a moment, I'll go through and spend a little time showing you how to do each one of these rays. Even though you could draw all three of these rays, in reality, you only have to draw two of them at any time, and that will help you locate the image. So I'll go ahead and draw 3 of them on my first example, but then I'll show you how you could go ahead and just draw 2 of them and still get the answer that you're looking for. So what we're going to do is look at the example on the next slide. So what I have right here is a pretty standard start to array diagram. The way you start off by drawing an array diagram is you typically draw a horizontal line on your paper that you label the principal axis. And this principal axis is meant to go through the very center of a lens, perpendicular to the lens at the center. And then on that principal axis, you typically draw the focal points that may exist for the lens. In this particular lens, what I have is a convex lens. So the way you draw a convex lens is you draw the shape of the convex lens on the principal axis. It doesn't really matter how thick you make the lens in the middle. That kind of is up to personal preference, because in reality what really matters is this dotted line, this dashed line that goes through the middle of the lens perpendicular to the principal axis. That line represents the points of refraction when you do the drawings here. You'll end up finding out that this really is a huge approximation in the lens, but it works out well enough to where the predictions of where images are still is good. So then, because I have a convex lens, I actually ended up drawing 2 focal points. Here's what you want to think about. If I had a light over here, right, and I was shining a light over here towards the lens, all of the light rays that went through this would focus through this point right here, right? So they'd go to this point, and all the light rays would go to that point. So there is a focal length on that side of the lens. Well, there's also a focal length on the other side of the lens too, because, you know, if I had a light that started over here, and I shot these light rays through that focal point, and this one right here, and you can see the point, it ends up focusing light on both sides of the lens. So you end up having 2 focal points. Okay, you're going to use both those focal points when you're drawing the ray diagrams. Finally, the last thing that you have is an object. Now, I don't know why in physics an arrow has always been chosen to be the object. I think it's because it's really easy to show it being upside down or right side up. But boy, it seems like they could have picked, you know, other objects to use, like a star or I don't know what. But anyway, arrows always end up being the objects that we use in these pictures. And so in this example, I have an arrow that's farther away from the lens than the focal point. And actually, I would want you to realize that it's more than 2 times farther away than the focal point. If you consider this as being the distance between the lens and the focal point, twice that distance is like right here somewhere, right? And I actually have the object outside of that. That's kind of an important thing for the object that we're going to be projecting an image of. So what I'm going to do is I'm going to go through and draw the ray diagrams that correspond to the rules here on the previous page. And so you might want to cross-reference these rules with the pictures while I'm drawing it. Okay, so the first ray that I'm going to draw goes like this. You take your ruler and you draw a line that goes from the top of the object, the arrow, and it goes parallel to the principal axis until it hits that dotted line. Okay? And then what would happen at that point is the light that goes along that path, based on the definition of a converging lens, will then bend through the focal point. So what you want to do is draw another line going from that point through the focal point, and then you want to extend it kind of far because you really don't know where the image is going to end up being, so you just go ahead and extend that line out pretty far. Okay, so that ray follows rule 1 on the previous page right there. Okay, so that's the first ray that we draw. Now the second ray that we draw goes from the top of the object, and it goes through the near focal point until it gets to the lens. Okay, so what you want to do is take your ruler, draw a straight line that goes from the top of the object through the closest focal point until it gets to the dotted line through the lens. By definition, the way that light will refract is when it hits that point, it will actually then move parallel to the principal axis off in that direction. So that ends up being ray number 2, according to the rules that we have listed up there. Okay, so the third ray is actually the ray that is actually kind of my personal favorite, because this ray pretty much works in all situations. You go back to the top of the object and you draw a ray that goes through the intersection of the principal axis and the lens. And the key thing on this is that that ray will just pass in a straight line, because when it refracts and refracts again, the geometry of it works out to where it just continues to go in a straight line, which is pretty cool. Well, you can see that if I continue that ray along in the right direction, it ends up intersecting with the other 2 rays in pretty much the exact same place. Okay, so that ray is ray 3, according to the rules on the previous page. Now, here's the key thing. You can see that you had 3 rays that started from the top of this object. This happens because light comes in from the sun or from other nearby lighting. It hits the top of the object and it just bounces off in a myriad of different directions. Well, 3 of the light rays that bounce off of that position actually follow this pathway until they get to the lens, and then you'll see they actually recombine together again at this point. What happens is your brain sees this intersection of points that carry the information from the top of this object, and they think that's where the top of the object is. And so your brain would actually reconstruct the information that is here in this position, which, again, like I said, is kind of a cool thing. Well, then technically I should go through and follow all of this process for every point along the way, but that's kind of a dumb thing to do, because it ends up being a lot of trouble, and we can just do one simple thing. If I took these 3 rules and I used the bottom of the object instead of the top of the object, you would find out that every single ray would end up going along the principal axis, right? Ray 1, ray 2, ray 3, which means the bottom of the object really could be anywhere along the principal axis. Your brain, from like a depth of field perspective and sort of thing, would put the bottom of the object basically right above the intersection of the points. Which basically means then that the image of that object is right here, okay? What this is an image that can actually be projected away from the lens, right? Notice that it's actually upside down as compared to the actual object itself, and it's actually smaller in height than the object itself is. If I go back and look at the diagrams that I'd shown you on the previous slide here, you can see that this is pretty much the same situation. You had an upright candle flame that was some distance away from the focal point. This lens projected a real image of it over on that piece of paper. Okay, this process kind of shows you how that would occur. Okay, so when we draw ray diagrams, part of the answer to this problem is not only drawing the picture to show where it is, but you also have to describe the image. So this image would be described as being a real image. It's real because it's actually formed out in space. You can project this image onto a piece of paper. Another way of thinking about it is that it's on the other side of the lens than the object is. This image is also inverted. That means it's upside down as compared to the original object. That's going to be pretty obvious from the picture you drew. And this image is smaller than the actual object. One way you could describe that more quantitatively is you could put a ruler on the image and measure its height, and then you could also measure the height of the object, and you could do like a percentage type of thing. But honestly, in most of the questions that I will give you or that you'll see in the future, you just want to say if it's larger or smaller. You know, this paper, this slide right here basically just kind of shows you what the difference between a real image is and a virtual image. And when you're trying to describe your final images, you just want to keep this in mind. A real image is going to be one where the refracted light rays actually do cross each other. Okay, this will be projected on a piece of paper or film. Cameras project real images on the film. The projector that you're looking at this presentation through is projecting a real image on the screen. There's actually like a small liquid crystal display screen inside of the projector, and the lens is just taking that image, that object, and projecting it as an image on the screen for you to see it. It's actually interesting if you look inside of the projector while it's on, which I wouldn't recommend doing because it's super bright light. But if you do that, you'll actually see the little liquid crystal display screen that's inside of there, and it's actually upside down so that you can see your image right side up. It's pretty funny. Well, anyway, that's what a real image is. And then a virtual image is one where the refracted light rays actually don't cross each other. So they don't actually really go across each other in real space, but when you carry them backwards, you see that they actually look like they're coming from a certain place. Back to that perspective drawing idea that I talked about. I'm going to show you an example here in just a moment on how to do a ray diagram where a virtual image gets made. Okay, so let's do that example right now. Now, what I did here is I took the same situation that we had before. I've got a converging lens where the lens is in the middle of the principal axis. I'm going to draw that dotted line that goes through the center of the lens and perpendicular to the principal axis. That's really the dotted line that represents like the lens itself, right? So all your refraction rays happen from there. And then I still also have focal points in front and in back. Now you'll notice I have the focal points farther away than I did before, and that was just so that I could put the object inside of the focal point. Now we can see how a virtual image gets made in this scenario. So I'm going to draw the same rays that I drew the first time, although one ray I'm going to have to do a little bit differently than I would have in the past. So the first ray from our ray diagram rules goes like this. I start from the top of the object and I go parallel to the principal axis until I get to the lens. Then when I get to the lens, that ray goes through the far focal point. Okay, so that's ray number 1. Okay, ray number 2 is supposed to go from the top of the object through the near focal point to the lens. And you can see right now I can't do that because I can't do a straight line that starts at the top, goes through the focal point, and then goes to the lens. However, what I can do is start at the top of the object and go away from the near focal point, right? I mean, really what I'm kind of doing here is it's almost like I'm starting at the focal point and going through the top, or to the top of the object to the actual lens itself. What it turns out is that as long as the focal point, the top of the object, and the lens are on a straight line, the ray diagram process still works. So when this ray gets to the top of, or when this ray gets to the lens, then it will refract parallel to the principal axis, like so. Okay. Now you can start to tell right now that these two light rays, these are the refracted rays. Those two light rays are never going to cross each other. Okay, they're diverging rays, which kind of lets me know that I'm not going to get a real image. However, if I follow back this refracted light ray straight backwards, and if I follow this refracted light ray straight backwards, you can see that they look like they're coming from a point right here. They look like those two light rays are coming from a common point. Well, that starts to give me the idea that that's where the image of this object is going to be. All right, well, I'm still going to draw the third ray because I really like that third ray. And that third ray, if you remember, goes from the top of the object through the lens, and it just goes in a straight line like always. Again, that third ray is diverging from these other two, so they're never going to actually cross each other in the real world. However, if I look where that ray seems to be coming from, if I draw it backwards, you'll see that it's emanating from the same common point that the other two were. So this place right here, this point of intersection, is where the image of the top of the object appears to be. So the image is actually larger than the object is. And this image is really what we would call a virtual image. It's a virtual image because it can't be projected on paper out here. It doesn't really exist in the real world. In order to see this image, I would have to actually place my eye over here and see the image over here in the background. This is basically what a magnifying glass does. If I take a converging lens and if I put it close enough to the object to where the object's actually inside of the focal point, then I basically just magnify the object and make it look bigger. And one of the bonuses is that it's upright, so I don't have to worry about seeing things upside down. So this image would be described as being virtual, upright, and larger. Okay, so the last thing for me to show you guys how to do is how to draw ray diagrams for a diverging lens. Okay, so a diverging lens is a little bit different because it doesn't really refract light through a point, it refracts it away from a point. And actually drawing the ray diagrams, you have to do a little bit of modification of the process, but in general you'll see what the similarities are. So, I start off by drawing a principal axis, and I draw a dotted line perpendicular to that, and then I went ahead and drew like a diverging lens here. It doesn't really matter like how curved you make the sides of the lens, because you're really just going to go to the dotted line. But honestly, that shape is just there so that people know that you're drawing a ray diagram for a diverging lens versus a converging lens. Okay, now one of the tricks here is that you still have to label something that acts like a focal point, right? So what I'm going to do here is I'm going to draw a dot on both sides of the lens, and I recognize that those aren't really focal points. This over here is actually like the diverging point for rays on the right side, and the point over here on the right side is really like the diverging point for the rays on the left side. Kind of a weird thing, but again, you'll sort of see how that works when I draw the ray diagrams. Okay, so now I've added in an object to this lens. You didn't have an object on your slides, so you should probably draw one in there. Doesn't really matter where I put it, doesn't really matter how tall I make it. I made it just be outside of the near side diverging point, and it happens to be almost taller than the lens, but again, it doesn't matter, just the way I'm doing this diagram, you'll see how it works out. So we are still going to follow the same rules that we followed before with just some minor twists. Okay, so the first ray goes from the top of the object to the lens until it hits the lens. But now, instead of going toward the near focal point, it's going to go away from the far focal point. Okay, so the simplest way for me to do that was to draw a straight line like so, and then you can see that this line is really going away from that focal point. Okay, I'm going to draw that backwards though a little bit, just because you need to know that line's there for our next ray. The next ray would go from the top of the object through the near focal point to the lens, but I actually need to involve the far focal point. So this is sort of weird. I'm going to go toward the far focal point, but instead of actually getting to the far focal point, I'm going to stop at the lens. And then when it gets to the lens, it goes parallel to the principal axis. Okay, well right away you can see these lines are diverging, and I think also right away you can see that the rays are probably going to meet somewhere back here in virtual space. If I carried this refracted ray backwards and met up with this refracted ray backwards, I end up getting a point that is right here. The key thing to understand is that the two rays that I'm drawing backwards are these two rays right here. Okay, those are the refracted rays, and so if I draw those backwards, they intersect at this point. There's a lot of clutter going on here, so you really have to keep those straight. Now the third ray, my favorite ray, still does the exact same thing it did before. It goes from the top of the object through the center of the lens, and then it just keeps on going. Well, this time it didn't turn out as well as it has in previous slides, but do you see how it's really intersecting with these all right here in the middle? Where all three of those rays intersect with each other is where the virtual image is. And so the image is formed at this point, and I actually couldn't make the image small enough. The computer wouldn't let me do that, but really this arrow should even be shorter than it is to fit in the space between the intersection and the principal axis. So again, if I had my eye over here and I was looking through that lens, okay, I would see an image that was smaller than the object, and it's also kind of interesting that it looks like it's closer to the lens than it really is. if we go back to this picture that I included early on in the slideshow, okay, right here, that's basically what we're looking at. Now, to say that it looks closer than it really is, I'm not sure the picture does it justice, but this is one of those things that when you actually do look through one of these kind of lenses, you'll be able to see that effect. It really changes like the depth of vision that you might be accustomed to. Okay, so draw an array diagram for a diverging lens like this. They're pretty much always going to look like this. Okay, it doesn't really matter where the object is. If it's inside the focal point, outside the focal point, you're still pretty much going to get an image that is like this. One of the things that does end up being kind of interesting is that the image starts to get closer to where the object is if the object is really close to the lens, and so you start getting more to like the true size and the true depth of field. If I was going to describe this image with the terms that I'm supposed to use, I would call this a virtual image that is upright and smaller. Okay guys, hey, we're almost done here. This is just about it. I've basically shown you how to draw array diagrams. The last thing to show you is that there is, of course, some math involved here. What we just did was a true approximation of how things would work out. But the thin lens equation will basically describe to us the exactness of how this will work. Now, this equation is really interesting because it looks like I'm adding stuff together, which you are very tempted to just think about then like value sizes and things like that with addition. But it's really important for you to see that we're actually adding inverses of things. And when we add the inverses, we get an answer that is actually the inverse of something else. So I'll go through an example to show you this and make sure you understand what's going on, but this is the equation that we use to do it. This would help you figure out where something is located. This would help you figure out DI, okay, the location of an image. And then the equation down below here is the one that actually would help you calculate the actual magnification. And really it ends up just being a ratio of distances, and it ends up being almost like a percentage, if you want to think about it that way. This negative sign is kind of important because when things are positive or negative, it'll tell you if they're real or virtual. So what I'm going to do is use one of the previous examples as an example here to do the math with. So I'm going to go back and actually use this first problem as an example. No, sorry. This first problem as an example so you can see how it works out. And in order to do that, I'm going to get rid of all the rays and everything that I drew. I am going to keep the image there just so we can check our final answer. Okay, what I would recommend you do is just write down the measurements of what I take in this picture on this slide right here where we do the example. Okay, so down in this space down below, I would just title this example. What I'm going to do is I'm going to measure DO, which is the object distance. That's the distance that the object is from the lens. I'll measure that with my on-screen ruler. That won't be the same as your ruler because my scaling is dependent upon my slide that I have on my computer screen. So I would just say you'll write down the distance that I measure, and you'll also measure down write down the focal length that I measure. And then we'll use those two values to solve the equation with the thin lens equation. So back to this example, I'm going to bring on an on-screen ruler, and I want that ruler to be, I don't know, I can just pick a scaling whatever I want. I'm going to make the ruler a little bit bigger just so that I can read the numbers a little bigger on the screen. And I'm going to take the ruler and I'm going to measure the distance from the object to the lens. When I do that here, it looks like I've got about 6.7 centimeters. So 6.7 centimeters is the object distance. Okay, so write that down on your piece of paper. Now, I'm also going to measure the distance from the focal length to the lens. So the focal length here looks like 2.7 centimeters. So write down F equals 2.7 centimeters on your paper. Alright, so what I've done is I've written down the object distance of 6.7 centimeters, and I've written down the focal length of 2.7 centimeters. The unit of measure here does not really matter. As long as they both have the same length units, then that's all that's important. So what I'm going to now do is I'm going to take these two values and I'm going to plug them into the thin lens equation like so. Okay, so I have 1 over 6.7 centimeters plus 1 over di equals 1 over 2.7 centimeters. What I'm going to now do is rearrange this equation algebraically so that I'm solving for 1 over di. So 1 over di will equal 1 over 2.7 centimeters minus 1 over 6.7 centimeters. Now, when you go to do this on your calculator, what I recommend doing is typing in 1 divided by 2.7 equal, and then minus 1 divided by 6.7. There also is a button on your calculator. It's an inverse button. It's called x to the minus 1. You could use that button as well, and that might make it a little bit simpler, but honestly, it's really just easiest to type it in the way that I described it a moment ago. So when you do that, you're going to end up getting a number that is 1 over di equals 0.2211. Now, that's not what di is. That's what 1 over di is. What I need to do is now perform one more function on this number so that I can get what di is, and that is I need to take 0.221 and divide it into 1, or I need to find the inverse of it, if you will. When I do that, I come up with di as being 4.5225 centimeters. Okay. Now, what I'm going to do is I'm going to go back and confirm this answer with the ray diagram that I had drawn originally back on this problem. So when I go back to my ray diagram picture, I'm going to take my ruler and I'm going to put it on my picture that I drew, and I'm going to measure the distance from the image to the lens. And you can see that I got like 4.45 or something like that, which is, you know, pretty darn close to the answer I calculated. And I would say that this answer that I calculated is actually the answer that I would actually trust. Okay, sorry, this all ends up going away from the slide. It makes it all go away again. But that's actually the answer that I would trust. I would say that that's mathematically really the correct answer. Okay, so that's how you can calculate where the image is. Now, you can also calculate the magnification, and the answer to the magnification tells me some other things about it too by using this simple relationship. If I just take the ratio of the di of the image distance to the object distance, I can find out what the magnification is. And so I'm going to do that over here in this spot on the paper. If I take negative di over do, so it's going to end up being negative 4.5225 over 6.7, I'm going to calculate this answer, which is negative 0.675. What that number tells me is three things, really. The 0.675 tells me that it's smaller than the object. It's about 67.5% of the height of the object. The negative sign tells me that it's a real image, and it tells me that it's inverted. Whenever you use the magnification equation, that negative sign kind of communicates that to you. And that really is just set up by convention ahead of time by putting the negative. The negative was really there to tell you if it was inverted or not. And then it also turns out that makes it real too. One thing to remember about all of this is that real images formed by lenses are always inverted. Okay, so that'll always be a negative sign there. And then virtual images formed by a singular lens is always upright. So a positive sign would mean virtual and upright. So you can see here that the math obviously goes a little quicker. It helps you to calculate things pretty fast, but I think the ray diagrams part helps you to visualize what's going on a little bit. So you really need to know how to do both. I'm going to give you some homework problems where you have to do both of them, and be prepared that when it is time to test on optics, that I'll have you do both of those. The homework assignment that I'm going to have you guys work on for this is out of chapter 23. There are 5 problems in the book that apply, and then also I'm going to give you a worksheet that has some already pre-done ray diagram setups, and then all you have to do is draw the rays. Don't forget that when you draw these ray diagrams, you also need to describe the image in the end as real or virtual, upright or inverted, or larger and smaller. Also for next class, guys, we are going to pick up with some more optics stuff, so I'll be teaching you some more things. You're going to need to print notes. Optics Lecture 3 should be available. I'll be back there, so not only will we do a lecture, but I'll also go over last night's homework, and I'll go over some of this homework. We'll have plenty to do. So anyway, hey guys, sorry I couldn't be there again today. It's kind of difficult to learn in this way, but it's good practice for you for down the road, because I think there'll be a lot of video and online learning in your lifetimes. So have a great day and good luck working on your homework.